these what you see are a few 12 volts DC motors. Now a DC motor is a variable current type of load, which means that the current keeps on changing as the load changes. Higher the load on the motor shaft, more is the current drawn by it. Next, what you see are a few incandescent bulbs which come under the category of constant current type of resistive loads. And the final ones that you see are the constant voltage loads, which are our electronic circuits and batteries. Now guys, all the above loads are rated at 12 volts, but let's assume that I only have a 20 volts 3 amps DC source. In case of the DC motors, their no load speed will increase because RPM is directly proportional to the input voltage. The impact will be its brushes will wear out faster than usual, its commutators will also wear out faster than usual. There is also going to be an additional heating which might affect the strength of magnets used in the motor. Now let's consider the case of what will happen if we connect a 20 volts supply to a 12 volts 1 amperes bulb. The bulb will fuse instantly because more than rated current will flow through the filament and burn it. Now comes the final test of connecting the 20 volts 3 amperes power supply to a 12 volts electronic circuit or a 12 volts battery. Both of them will get damaged because the battery will get overcharged with time and the electronic circuits are too much voltage specific. So keeping all that in mind, we can conclude that we need to build a 12 volts circuit. Let's get started. First component is 13009 power transistor, second one is CTC1351, third one are diodes, Zener diodes, 1.8 volts each, and the fourth final one is 1 kilo ohm resistor, and final heat sinks and few wires. That's it. Now comes the construction of the circuit. Take the 13009 power transistor and bend its 3 terminals as shown. Next, do the same thing with the NPN 1351 power transistor. Next comes the placing of thermal paste or heat sink compound on the power transistor. Okay, this is how it is going to transfer all the heat safely to the heat sink. Place it on both the transistors. Now comes the part of mounting the 2 transistors on the heat sink. So here, as you can see, that I'm going to use a single heat sink and I'm going to mount both the transistor on a single piece. You can use 2 heat sinks, separate heat sinks, for cooling it further, but I think it is not going to generate much of heat. Now take the 2 Zener diodes and shorten up their terminal ends by cutting them. After that, connect the 2 Zener diodes in series. Like one Zener diode is at 1.8 volts. So if we connect 2 of them together in series, it's going to be 3.6 volts DC. Now take the positive end of the Zener diode and connect it to the base terminal of the 1351 power transistor. Now solder the base of 13009 power transistor to the emitter of 1351 power transistor. After that, take a wire and connect it to the emitter terminal of 13009 power transistor. Now comes the collector terminals of both the transistors. These 2 collector terminals will be soldered together, and this point is going to be the tapping point at which multiple connections will be made. Take another wire and connect it to the collector, common collector of both the transistors. Now bend the Zener diodes and connect their negative set to the collector as well. This is how you're going to do it. Now hold the green wire as shown here and place it through the screw hole of the heat sink. Now you will need another wire, a different colored one. Strip it and then place it through the other screw hole of the heat sink. Lastly, strip the 2 wires in the middle and connect the 1 kilo ohm resistor to the 2 wires. Please note that the links for all the needed components have been provided in the description, so don't forget to check them out if you really want to make this circuit. So well done guys, it's finally time to test it. This is the laptop charger connected to the 220 volts supply, and this laptop charger is converting 220 volts AC to 20 volts DC. So what I'm going to do is convert that 20 volts DC to 12 volts DC, although the output is going to be a little higher so that there is a charge difference and current can flow easily. And remember that this green wire here is positive and yellow one is negative. Red clip will be connected to the green because red is always denoted by positive, and yellow one will be negative, and we are done. Now let's do the measurement of output voltage first. So pointing the meter towards DC voltage measurement mode. Okay. You can see there is some voltage being deflected because of one wire connection. And now we have our full 13.09 volts DC out from the laptop charger by using just this circuit. No transformer is needed. All you got to do is just do this. It is very simple and safe, and the output voltage is pretty accurate. So the voltage testing is done. Now comes the LED panel glowing test. So this is a 12 volts LED panel, and obviously it would have burnt out or got fused if I had connected this panel directly to the laptop charger, since this is 12 volts and this is 20 volts. So I have converted it safely to 12 volts. Let's see how it performs. And here we have 20 volts beautifully converted to 13 volts, exactly needed for this. Let's turn off the lights. All the lights have been turned off, and you can see that it is glowing really bright, and also there is negligible heating because this driving transistor is rated at 12 amperes and also connected to a good heatsink with heatsink compound or thermal paste, so it should not be a problem. Turned off the camera lights as well, and now it is even more bright. See, pretty good, right? So let's increase the loads now. This is a 12 volts 35 watts bike headlamp bulb. Let's try this one. Let's turn off the lights. You see, it is glowing pretty bright. Moving on to an even bigger bulb. You see 12 volts 100 watts. That's big one for car headlamp. Let's turn off all the lights. Now guys comes this high current DC motor. It is 12 volts 5 amperes, really smooth. So let's test this one. Initially it was running on 20 volts, so the RPM was higher, but now it is running at the exact needed RPM. So guys, I have removed the jumper cables and I have connected the circuit directly to the laptop charger. Meter is showing 0 volts DC, and let's measure the battery voltage, which as you can see is around 12.54 volts. Now let's connect the jumper cables here and then see the change in voltage. At present it is 12.54 volts, and you can see that it is safely increasing. And we can leave it like this. So guys, your question for today is, what was the maximum RPM displayed by the tachometer in my previous project video? Well guys, you can also carry out the same process on a 20 volts solar panel. Okay, that's the battery meter and my circuit. Here as you can see guys, that the voltage is increasing. 12.47, 48 and so on. So the increase in voltage is indicating here that the battery is charging with the solar panel, and it is really safe because this circuit is going to limit the output voltage to around 13.2 or 13.3 volts DC. So you can even leave the battery so that it keeps on charging all the time, and when it is fully charged, then the current from the circuit is automatically going to reduce to zero. These four what you see are high current DC motors. All of them are rated at 12 volts, but we have to find out the maximum current rating. This one you can see the coil inside, how thick the copper wire is, and the commutators. So here I'm going to use this 12 volts 7Ah UPS battery to find out the maximum starting and running current. Running current, as you can see, is around 2 amperes, while the starting current peak is up to 5 amperes. So that's the high current. Now let's open it all up and see how the armature and the magnets look from inside, and if it contains ball bearings or bushes. Now guys, we also have to make a permanent mark because it is going to be difficult otherwise when we close it after viewing the inside parts. So it is open now, and that's the armature. Let's close it up. So guys, as you can see that the copper wires are really thick, and yeah, it's like new from inside, although it looked not so much new from outside. The magnets are also in good condition, no problem with that, and the brushes are also very healthy, okay, and pretty big brushes have been used to carry that huge current. So let's measure the wire thickness. You can see it's almost 1 mm. Now let's place it all back. The wire thickness is 1 mm, no wonder it can carry huge current. So guys, in this video I'm not going to do the motoring mode tests but the generator mode testing, okay. Let's place the screws and keep them held tightly, and also place some WD-40 because it has bushes and not bearings, okay. And this motor that I am placing WD-40 on, this is the piece I'm going to use for testing. This is a large 1 kilowatt DC motor, and this is a small motor, and this is a double groove pulley which I got from Banggood. Link will be in the description if you want to buy it. And it has like the bolt to tighten up, and it is 8 mm and fits perfectly to the shaft size of the motor. So let's place the rubber belts and I'm going to use two of them because this small motor and the big motor both are going to be under huge load, because I'm going to do the maximum power testing here. So those two terminals, brass terminals that you see, to those I have connected two wires, and to the wire output I'm going to connect the multimeter pins to measure the voltage it is generating when I run it at high RPM with the help of the large DC motor. This is the DC motor speed controller that I made, and a low high speed and DC socket. So let's do it with one belt at the start. As you can see, it is producing around 5.2 volts. Let's increase the voltage. Yeah, its performance voltage has increased to around 9 volts, even 10, close to 12, and we have crossed 12 volts. 13.24 volts was the max we got. Okay, so the output voltage, generated voltage, was pretty good. So here, as you can see, that I've given two more wire connections to connect few bulbs and other loads to it. So first I'm going to start with a 6 volts bulb. You see, 30 watts 6 volts bulb with two filaments. It's from a Royal Enfield. Okay, wait a second, it's moving, and you can see that it is glowing brightly, really bright. And obviously it is really easy for the small generator to light it up, and the voltage is around 7 volts, so the bulb is glowing at its full potential. Now this you are familiar with is 12 volts 35 watts bike headlamp bulb. Okay, so let's connect this one, and this one is also lighting up brightly with a little more drop, as can be seen on the multimeter display. The voltage is dropping. Let's increase it to 12 volts by increasing the driving motor RPM. We have reached around 9.5, 10.5, and we are doing around 12 volts. Yeah, around 13 volts was the max we did. And you can see that I've removed the input supply socket, and it is still running because of the flywheel. Okay, now let's move on to even higher power bulb, 90 watts, 100 to 90 watts, 12 volts. Okay, so that has also been connected. This is going to draw even more current, but first we are doing the voltage test right now. Let's see if it can produce that much voltage at such a high load. The load is really big right now for the small generator, and we have reached around 12.5 volts. Yes, the small generator is performing really good. And again, we have disconnected the supply, and still it is running because of the inertia disc on the driving motor. You see how long it takes to stop because of the large inertia disc. It is really helpful in that. Now enough with the voltage test. Let's move on to the current testing. You can see that I've pointed the meter towards 600 ampere current mode, pointing 0, flashing 0 at the moment. Let's place the multimeter at a point that it is visible pretty good, and the current drawn is around 4 amperes. It is the bulb is drawing. Let's increase it further. We have reached around 5 amperes, 5.5, and 6 amps. The bulb is glowing really bright, and we are peaking at around 6.06 amperes with the maximum voltage of around 12 volts. Here, the Starlight 250 watts bulb. This is a really big, it looks small, but it is really big. The filaments are really thick. Now I'm going to power up this 250 watts bulb. This is the biggest DC bulb I've got here. You can see that at the lowest input it is producing consuming around 3.5 amps. Let's increase it further. Yeah, we have reached around 4.5 amperes, so somewhat equivalent to the previous bulb, which was 90 watts, and we have reached around 6 amperes. We have crossed the amp rating of the previous bulb. Yeah, 6.27 amps for this one. The amperes were less because that was a 24 volts bulb. Now guys, comes the final shunt resistance short circuit testing. So I'm going to short circuit the wires with the help of an external shunt resistance. Okay, I've given really small loops, and at present at the minimum RPM it is drawing around 5.5 amperes and glowing hot. Okay, it's almost red. 5.5 amperes, increasing the RPM, and we have easily reached around 8.5 amperes and it is smoking red hot. Let's go further and see what happens. Okay, it has caught fire now. That is amazing. Oops, the filament burned out and it broke. The shunt resistance burned out. Now guys, comes the final test for which you all have been waiting, that I said that I'm going to do the maximum power testing. So we have done the maximum voltage testing, that was around 13.24 at the beginning. So now I'm going to go for the short circuit current testing. Now I'm not going to connect any shunt resistance, but I'm going to connect the two wires coming out from the DC generator so that it creates a shortest path short circuit. That is what it means. And at the lowest RPM it is producing around 11 amperes. It's the negative sign. Let's reverse the wire. Yeah, and now it is positive and 11 point, yeah, almost 12 amperes. That is pretty good at such a low RPM. Increasing the knob and RPM will easily reach around 20 amps, 22, 23. I don't think the belts can survive more. Okay, so I will have to turn it off. And the peak was around 25 amperes. Well, this DC motor is rated at a max of around 32 amperes. So yeah, the performance was really good.